Yeah, sorry. Okay, my name is Frank McCoy. I'm a postdoc at the Initiative in Digital Economy. And was saying some kind of also postdoc at the IDB.
I'm Deborah Soule. I was research associate at IDB and Center for Digital Systems. I'm Kristen Blacker. I'm in the Office of Executive Education at work. I'm Susie
Ben Schiller, econ professor at Brandeis. Hi everyone, I'm Sean Pond at Sloan.
Hi everyone, I'm Daniel Robb. I'm a second year PhD student. I'm Frank Nagel. I'm a doctoral student at ACS in the technology operations. Michael,
Avinash is student.
John.
Nima postdoc at UCS and stuff. I'm Justin Lockwood with the Initiative on the Digital Economy. So I'm here with Jeremy Howard, formerly president of Kaggle, moved on now to Analytics. He's doing a bit of an MIT World Tour this past week. So now I have an audience. I encourage you to ask questions and get involved. So Jeremy, whenever you're ready.
Thank you. Let me start in 1999. If you're using the internet in 1999, we're using Yahoo, or at least 80% of the time you were, according to market share statistics. Yahoo is popular because Yahoo employs excellent editors, people who spend all of their time being paid to surf the internet. And as they surf the internet, they find interesting places to go. And when they do so, they use Yahoo systems to put that place to go inside their huge taxonomy. This is the first two layers of it here. This is a great way for us to find interesting and useful things on the internet. So when this quirky company came along in 1999 and said, we're going to replace these human experts with a mathematical equation and a web robot which will surf the web on our behalf, and a mathematical equation that will decide what's interesting. The immediate reaction was pretty skeptical amongst the folks at IU, because the idea that a mathematical equation would be better than people at finding interesting things to read sounded like a crazy idea. As it turned out, it worked out okay. Similar crazy ideas have, for example, occurred in finance. Over 20 years ago, I built an equation that would determine which people applying for a loan would be likely to pay it back. At the time, most people looking at this question employed loan auditors who were experts at human behavior and could figure out with a high degree of certainty who was likely to pay back their loan and who wasn't. And so when I suggested that perhaps this could be replaced with a computer equation, again, that received a lot of pushback. And yet today, nearly all consumer loans are indeed judged using algorithms, not people. Really, the person to thank for all this kind of stuff is this guy, Arthur Samuel, who invented the area of machine learning. And he basically is the guy who came up with the idea that if we want to program something which we don't know how to do it ourselves, instead what we can do is tell the computer what we want and see if the computer can figure out how to get there. And this is what is today called machine learning. He developed this idea in 1956. He developed the idea in 1956 in order that he could create a computer program that was better than him at playing checkers. So he described to the computer the various ways in which one could play checkers, had the computer play against itself thousands of times so that it could find the values of those parameters that worked well, and soon enough the computer was able to beat him. And by 1962, the computer was able to beat the Connecticut state champion. So machine learning is an area with quite a lot of history, quite a lot of successful history, and today is very widely used in industry. Anytime a computer does something which is like creepily good, it's probably doing machine learning. So when LinkedIn and Facebook tell you who your friends are, it's not because somebody's programmed the rules to do that, it's because somebody has described the goal of this and had it figure it out from the data directly using machine learning. When Watson figured out how to answer subtle questions like this one, it's not because somebody programmed the rules of how to play Watson, but because, how to play Jeopardy, but because IBM developed a machine learning algorithm which did things like ingest the entirety of Wikipedia and understand the nuanced and subtle kind of patterns that are involved in answering questions like this, again using machine learning. So how many of you guys are familiar already with what Kaggle is? Not everybody. Okay, so Kaggle's the world's largest data science community. There's about 180,000 data scientists who compete to solve machine learning problems. And so I was president of this until about a year ago. Hundreds of problems were solved for the first time. And this is an example of a kind of classic machine learning application in industry, which was a competition run for Allstate, looking at can you predict for each new applicant what their dollars of claims are likely to be. This is for car insurance. And in this competition, the Kaggle community came up with an algorithm that was 270% more predictive than Allstate's actuarial team's algorithm in a 3-month period. Again, the reason for this was that they used modern machine learning methods rather than the more classical actuarial science methods that had been used until that time. So machine learning is now increasingly being used in industry for things like this. I was lucky enough to have a chance to learn a whole bunch while I was at Kaggle about, what kinds of problems are people trying to solve with machine learning and what kind of techniques are some of the best people using. And something interesting happened for me in late 2012, which was we ran this competition for Merck, which was looking at predicting which molecules would turn out to be toxic. This is basically part of an automated drug discovery system. And something interesting happened in the competition. The winners, not only did they outperform all previous known algorithms in the academic chemoinformatics literature and the algorithms that Merck themselves have developed in-house, but they entered the competition only 2 weeks before it finished. And not only did they win, but they actually won quite easily, which is unusual in Kaggle competitions. Normally, a whole bunch of people tend to get about the same score. It's kind of like in a 100 meters race where it's like, 0.01 seconds separates first and third. This wasn't the case here. These guys flew out to the front. None of them had any background in chemistry or biology or medicine or life sciences. So I was interested to find out how they had done this. And the answer was, it turned out that they had used a new technique for this area, something that hadn't been applied to chemoinformatics before, although the technique had been around for a while, which is called deep learning. How many people have heard of or come across deep learning? Okay, so for those of you that haven't, it's basically a kind of an evolution of neural networks, which most of you would have heard of. Neural networks were pretty disappointing in the 1990s. They had a lot of promise, but never quite did anything that exciting. But in computer vision, they had started to do some interesting things. For example, in 1996, they were used for often for reading checks. About 10% of America's checks were read using deep learning algorithms. But the interesting thing here was that deep learning was being used for something totally different, which is chemoinformatics. It's like a really classic kind of data analysis problem. You just have columns and rows of data, kind of much like you would see in industry all the time. It was unusual to see deep learning used in this way. In fact, it was interesting enough that the New York Times actually wrote a front-page article about deep learning about 2 months later in which they highlighted two things, one of which was the competition-winning algorithm, and this is the guy that led the team, Geoffrey Hinton. He's actually one of the guys that's kind of the father, actually, of deep learning. The other thing that they highlighted in this article was Microsoft demonstrating a really interesting application of deep learning, which I will show you. To get the audio to work, do I have to do anything other than just plug this in?
It's a good try.
Okay, so see if you can hear this.
Now, the last step that I want to be able to take in this process is to actually speak to you in Chinese. Now, the key thing there is we've been able to take a large amount of information.
So he's talking in China at a academic conference in machine learning and image processing. As he speaks, on the left here you see his words appearing on the screen. A deep learning algorithm is doing that transcription. Over here you'll see the Chinese translation. That all translation is also being translated using a deep learning algorithm.
From many Chinese speakers and produce a text-to-speech system that takes Chinese text and converts it into Chinese language. And then we've taken an hour or so of my own group, and we've used that to modulate the standard text-to-speech system so it would sound like me. So what you see now is the result of that change. I'm speaking in English, and hopefully you'll hear me speak in Chinese in my own voice. Again, the results were not perfect. There were in fact quite a few errors. There's enough work to be done in this area.
So, you can kind of hear from the Chinese audience at first there's this kind of muted kind of like, wow, did that really happen? And then the second sentence there's actual cheering, which doesn't always happen in academic conferences. Not even when I speak, funnily enough. So, this is interesting to see in 2012 being highlighted that there's this one algorithm that's doing speech recognition, translation, phoneme creation, chemoinformatics, and had already been known for doing things like reading digits and checks. So it was at that point that I started taking a really serious interest in deep learning. I, like many people, had spent time in the early 90s looking at neural networks and had kind of put them aside for a long time. And I thought, wow, it looks like things have been developing in my absence. So I started looking to see what had been happening. And one of the things I discovered was that in 2011, a small and not very well-known competition had been run in Germany that was looking at traffic signs like these ones. And the competition was, pretty standard in many ways. But what was really interesting was that when I had a look at the results of this competition, I discovered something really interesting, which is that one of the teams in the competition results was human performance. And human performance had a error rate of 1.2%. And the best machine learning result from ITSIA, which is a Swiss research institute, had an error of 0.5%. I thought this was pretty extraordinary because I hadn't seen before a situation where machine learning had actually outperformed humans. That's something that humans traditionally have done much better than computers, which is to look at things. And it kind of got me thinking, what are all the things that we do as humans now because we're better at perception than computers? So as I started thinking more about this, more stuff started happening in 2012. A whole bunch of stuff started appearing. Another New York Times front page article appeared about deep learning that was focusing on this work that came out of Google. And what Google did was that they looked at about a week's worth of YouTube videos. And they said, okay, humans don't learn about the world by having little labels appear on top of everything we're seeing all the time and learning this is a person, this is a chair, this is a door. I wonder if computers can learn the same way that humans can just by, in this case, watching movies. So they took a week of YouTube and they put that through a deep learning neural network and ran it on 16,000 computers for about a month to see what happened, see what came out. And out of then the 600 million or so neurons, they looked inside to see what these neurons have learned. And these are examples of the actual things that the neurons learned. Here's one of the neurons, here's another of the neurons, and this is not that they were told to look for cats or look for people. It had independently discovered these concepts. So Google actually went on to say, that's interesting, I wonder if we can now take these learned concepts and use them for an actual useful purpose, which is to actually do some labeled object detection. And it turned out to work pretty well. These are actual examples of photos that were successfully labeled by the system that Google created. The system had about a 50% accuracy level based on this 16,000 computer trained system. And at the time, that was, really considered pretty damn good. What I find really interesting, though, is what's happened since then. So also in 2012, the father of deep learning, that guy I showed you before, Geoffrey Hinton, entered what's called the ImageNet competition. The ImageNet competition takes pictures like these ones and asks people to design an algorithm to classify them in terms of, like, what is that actually a picture of? And Geoffrey Hinton entered the competition for the first time in 2012. And you can see that the error rate, basically the error rate had been flat for a long time. And in 2012, it suddenly dropped by a long way because of his use of deep learning for the first time. So basically when this happened, everybody I know in academia in machine vision stopped what they were doing, quite literally, and started looking into deep learning instead. And so since 2012, we've seen jumps of about a 50% improvement in accuracy every year. We are now down, 2014, to a 6.5% error rate in computer vision. And these algorithms now are generally trained on one computer for a few days. So in the last few years, 3 or 4 years, we've seen an increase in accuracy of about 10 times and an increase in speed of about 10,000 times in computer vision. So this is really interesting, and I thought I might try and show you a little bit about how this actually works. Right? So what these neural networks do is, I'm not going to go into detail of how neural networks work, probably quite a few if you have some sense of it. I mean, basically they are simple linear classifiers with some simple nonlinearities that feed in layer upon layer upon layer. So each layer of a neural network is extremely simple. This is an example. What you then do, though, is you run a convex optimization algorithm to find the weights for these kind of like linear classifiers with very simple nonlinearity stuff on top of them. Find the weights which give you the best predicted accuracy. And because you've got layers feeding into layers feeding into layers, the optimization algorithm is able to find simple features in the first layer which feed into more complex features in the second layer and more complex features in that in the third layer and so forth. Not that anybody's explicitly doing it that way, just the optimization algorithm figures out for itself that's the best way to do it. So these are some examples in the very first layer of one of the world's top performing neural networks, the image recognition. And what these are is they're little like 9 by 9 or 7 by 7 little pixel image patches. And you can see it's kind of looking for little diagonals or changes of gradient and color. And then over here on the right are examples of parts of actual images that this neuron here, for example, these are examples of actual images that that particular neuron fires on. This neuron here, here's some examples of actual images that this neuron fires on, and so forth. So a neural network then can take this layer 1 set of features and put them together into a second level of the network to create these slightly more complex features. And you can see, so for example, these features here are triggered by these little patches of real photos. These features here are triggering these little patches of real photos. So you can see even with this level of features, we could kind of describe something saying, oh, there's something that looks kind of like a sunset at the top, and underneath that there's something that kind of has some nice flat colorful areas and so on and so forth. So you could kind of compress your description of a photo using these features. But then as we then get into layer 3, it creates features out of those more complex features. And you can see really at each level they're getting like exponentially more complex in terms of what they describe. So these features in the top left here are finding kind of grids and honeycombs. These kind of features over here are finding the kinds of edges that appear on animals. These kind of features here are kind of finding the kinds of textures that appear on plants, and so forth. So it's pretty cool, you know, and we'll keep going, but I'll just do one more set of 2 layers. Once you start combining those, you start getting pictures of dogs' faces, for example, or pictures of round human-made things, so on and so forth, or pictures of the bottom of gangly-legged creatures. And once you get to layer 5, you're really now starting to find quite specific types of dog or quite specific types of showerhead or so on and so forth. So you can see that this very naive, simple mathematical approach has the ability to calculate complex features that depend on slightly less complex features and slightly less complex features. Real-world deep networks tend to have about 11 layers. And that's what it takes to create something with a 6.5% error rate at understanding what the world looks like.
Jeremy, I have a very silly question. Is there anything special about the 3x3, structure? And why is it 3x3? Is
3x3?
I mean, is each of those squares?
Oh, no, these are just examples, just to show you. Okay. Yeah, this is just a representation. There's like 600 million neurons in an actual neural network.
What is actually the difference between deep learning and neural networks?
Deep learning is a type of neural network. You could classify, one way of classifying neural networks into single hidden layer networks versus deep networks. So deep learning simply means more than one hidden layer. It turns out that only having one hidden layer in neural network requires exponentially more neurons to replicate more complex structures, whereas deep neural networks actually can explain exponentially more with additional layers. So that's why there was this small change to the structure has totally changed what they can do. The other interesting thing about deep learning neural networks is that the more data and computation time you give them, the more accurate they become, and we're not aware of any theoretical or empirical limitation in terms of how far that can go. So we had something similar happening in language. Google has released something called Word2Vec, which anybody can now download for free, which is kind of the equivalent of the first layer of features in an image network. This is basically 1,000-dimensional vectors that represent all of the ways in which every word in the English language, in fact over 2.5 million concepts in English, is used. So just like we saw the image examples before of having kind of features which can be built on to create very complex understanding of what images contain, Google has created the same thing for words, these complex mathematical objects which were learnt by reading 100 billion words of books, feeding them into a deep learning neural network, and then making these semantic features about words available. And people are now using these and things like these to do amazing things with language. So, for example, Stanford has produced a tool using these word vectors combined with a recursive neural network, which can take a sentence like this one. This movie doesn't care about cleverness, wit, or any other kind of intelligent humor, and can tell you that it is a negative sentiment. Red means negative. This is something which, before these kinds of techniques, we weren't able to get computers to read and understand at this level. In fact, we now have algorithms that can tell you what a sentence is about, what the relationships between the objects in that sentence are, which other sentences are semantically similar to it, what the overall sentiment of the sentence is, and so forth. So using these techniques, we can do similar things to language that we can do to images. We can even bring the two together. This is a little example that we've got at Analytic, where we can show you kind of the real-time search for words. These images don't have any text associated with them in our database, so this is doing a deep learning search, taking the representation of a bird in neural network space and finding the images in neural network space that are similar. But because we can combine words into phrases and sentences, we can start to do more and more with this. So we can go from bird to birds. We can even go from birds to birds on water, for example. And, you could do that kind of thing in Google Images. You could say horse in front of fence and look at the images, and it's like, oh, that seems clever. But, of course, it's totally cheating because the website says this is a horse in front of a fence, and it's just searching for text. So it gets much more interesting when you can actually understand images. If you think about it, for humans, we get most of our information through images and, to a slightly lesser extent, through language. So now that computers are around about equal to, in some places better than, in some places worse than humans at seeing things, and are not quite there, but approaching, and will probably pass in 2 years' time, humans at reading and understanding natural language. That's very interesting to think then about how does this change, the role of computers in what we can have them do. Computers can't only read language, they can also write language. Here's an example of an actual article in Forbes that was not written by a human, but written by an algorithm, the narrative science Quill algorithm. So we now have algorithmically generated stories that are of a quality high enough to put in Forbes, even if not high enough to put in The Economist yet, but maybe a couple more years. Yes. So the input to this is an earnings report, and the output is a piece of prose. Like how Forbes gave it a bio, too. Yeah, well, fair enough. If you don't, the computer will come after you. In fact, something else I'm going to show you is Baidu has a pretty cool example of what you can do with deep learning on their website. For those of you that don't know, Baidu is the kind of Chinese Google. I really like this one. Look at this creepy dog. So this is going to put the creepy dog into a deep learning algorithm and find other images in Baidu search which have similar deep learning representations. And you can see, I took this straight off my computer, right? So clearly they're not using anything about the metadata or the text, and yet it's been able to find other similarly colored, similar animals looking towards and slightly to the left of the camera, including some with creepy eyes. Yeah, that one's creepy. I'll show one more here. This can actually be quite fun. So anybody can play with this, stu.baidu.com. So this like kind of lets you find out like this picture actually clearly, not all of these are actual real world pictures of trucks apparently. I don't know why they fit this one back to front. And if they can recognize actually, you know, what it is, I think this one they can. They'll tell you that as well. Yeah, okay. So here they've said this is a golden retriever, various types of golden retriever. So you can click on one of those and get more information about that. So you can see it's successfully picked out exactly what kind of animal it is, and it's then shown us other pictures of the same breed with a very similar angle, including with their tongues out and so forth. If you think about what this means in medicine, so nowadays my focus is on medical applications, there's something very interesting, right, that we now have the ability to say, okay, let's take your medical data, right, your MRIs, your CT, your pathology slides, your lab tests, you know, so on and so forth, and let's use that exact kind of technology, combining the text and the images and so forth together, and that similarity search to identify, you know, out of the 100 million patients, here are 50 which look exactly like you in terms of what's about to happen to you. So, you know, what's about to happen to you has already happened to somebody else. And, you know, for half of them, this intervention was tried, and these guys lived, and those guys didn't. You know, but you can see there's like a truly personalized medicine that can come out of this, which is totally different to the kind of narrative style of medicine that we have today. And so this is what really excites me. There's actually some of this going on already. Some work that's come out of Harvard and Brigham and Women's Hospital. This one is a couple of months ago. It was actually written up in Nature. They actually looked at this kind of machine learning approach to analyzing tumors, and they discovered over 6,000 new ways of thinking about tumors, that, many of which are clinically relevant and have never been discovered before, by basically applying you know, this kind of machine learning technology directly to the images and removing all of the medical assumptions. So that's kind of in a radiology vein. Something similar in a pathology vein, which is like looking at the slides of tissue. Again, this is work that's come out of Boston area from Andy Beck and colleagues, was looking at using machine learning approaches to analyze pathology slides to find out characteristics of slides that are associated with cancer. And using this technique, they discovered a system that can identify cancer more accurately than human pathologists can. Again, they looked at about 6,700 features simultaneously in order to do this. This is known as the computational pathologist model. Really, really interesting. Some work that came out of Switzerland. This is, again, looking at pathology slides. So these are the slices of breast cancer tissue. Generally speaking, people assess breast cancer by saying, okay, how many, well, there's a number of factors. One of them is how many areas of high mitotic activity are there? So how many areas are there where the cells are rapidly dividing? And the pathologist here is marked in green all of the areas on these slides that have high mitotic activity. This work that came out of ITSIA in Switzerland actually fed this, about 70 of these slides, to a deep learning algorithm. And there were no medical features involved. No pathologist came along and said, this is how I would look at this. They just used the raw pixels, threw them straight into a deep learning algorithm, and got an 86% accurate algorithm that's about as accurate as a human pathologist. Yes?
I'm curious, is this completely replacing the human judgment? So what I'm really getting at is if you were to sort of take sort of a model averaging approach and put in the computer's prediction and humans' prediction, would the weight on the human's prediction go to 0?
No, certainly not at the moment. At the moment, it seems that the combination of human plus machine is going to be better. And this is the basis on which my company is operating, is we are trying to create decision support systems for positions that make them more powerful. So, for example, what Andy Beck's team is now doing is they're starting to look at images which are far too complex for any human to interpret by looking at like dyeing them in many ways simultaneously and creating these like incredibly complex, many colored images, many dimensions. To see what, whether a computer, my guess is that this will work really well, a computer will probably find more information in them than a human can see in those because there is a lot more information. So there are things that we're now at a point of saying, okay, what are the things that a computer can do that a human absolutely can't do, like a whole new level of vision. But then what a human can do is inject their kind of understanding of the systemization of disease, the kind of, or the history of disease. And they can also do more interactive things, so they could ask the patient something that would actually change the way they think about this. So at the moment, my view is that probably combining the two is going to be significantly better than either one on its own. There's no reason to think that will always be the case, however. And I'll get to that in a moment. Before I do, I just want to talk a bit more about things that are happening right now. For those that haven't seen it, there's this very cool website called Iodine, which came out about a month ago. And there's another really cool example of what happens when we just use the data that's already out there. So they're looking at hundreds of thousands of people's personal reports about their experiences with various medications. And you can go here and type in any medication and any usage, and it will tell you what people are saying about their experiences with that particular medication has worked for them. That's quite interesting. When we do things in this data-driven way, we can kind of treat the world as one giant randomized experiment. These guys actually aren't using machine learning for this. I think if they use machine learning, perhaps they will at some point, we could take this even further. To your question about, what might this mean, where do humans get involved? Let's go back a little bit and first of all say, what are people doing right now? Not just doctors, but what are people doing overall? And if you look at the labor force statistics, these dark blue areas are places in the world where the service sector is over 80% of employment. So that is, as you can see, all of the Western world is in that color. And so I kind of start thinking, well, what do we mean when we say the services sector? And so Eric and Andy McAfee and I have started talking about this in a lot more detail recently and trying to really understand in detail, if you look into the ONET statistics, what does it actually mean when we talk about the services sector. But, we're kind of talking about things like this. Things like reading and writing and speaking and listening and looking at things are the very things which computers in the last 3 years have started approaching or passing human capabilities at. Machines have always been good at integrating knowledge. That's something that they're super good at because they can analyze 500 million things at once, whereas humans can really have to focus a lot more. So if you think about, for example, preparing food, there is now a startup in San Francisco, I think it's in San Francisco, which can prepare a hamburger from start to scratch, right? And because they're preparing a hamburger, there are some difficult tasks like chopping a tomato, and they're difficult because they require combining pretty good vision and, some not particularly good, but, reasonable manual dexterity. So as soon as you come along and say, hey, we've now got computers that can see, suddenly chopping a tomato becomes pretty trivial, actually. And so now we're putting these things together, and you see there now exists a company that produces a end-to-end complete hamburger creating robot. And preparing food is something like the third most common job in America. Yes.
How expensive is that hamburger?
Well, you would say the marginal cost of the hamburger is almost zero. So actually the question is what's the volume at which they're produced, because the capital cost, well, it needn't be that high actually. The cost of these algorithms is basically, again, zero marginal cost for the algorithms. So I would expect, those robots to get down to a point at which they're used for the vast majority of food prep within a few years. There's no piece of them that is relying on a scarce supply-side resource, if you think about it that way. The cool bit is the software, and the software is infinitely copyable for free. So the key thing, and this is coming back to your question, is about where do humans versus computers fit into this economy. And so kind of humans do get better at stuff over time, at some kind of rate. We know that, however, deep learning in particular gets better in line with improvements with access to data and access to computational resources. Now, both of those things are increasing exponentially. We know that empirically. So this is what the kind of machine learning performance curve looks like. And based on what I can see in the kind of the capabilities and skills and jobs I'm looking at, I think we're about here, right? And until very recently, we were kind of here, right? So when I talk to, so I do quite a lot of executive education at Singularity University, and when I talk to people that run really big companies, because the last time they really looked into analytics in depth was when we were kind of around here, generally they'll be like, oh yeah, we tried using machine learning for something 8 years ago and it was a total disappointment. So I think we will be somewhere up here before the vast majority of people running companies noticed it happened. And so I think, I find it interesting looking at academia or looking at machine learning competitions because you kind of get a sense of what's, where are they up to, so where will we be in 3 years' time? So this is the thing that makes it very hard to use kind of traditional economic analysis, which generally relies on looking at the past and extrapolating to the future. This is kind of creating something of a qualitative shift. We have, of course, had something of a qualitative shift before, which was the Industrial Revolution. Before the Industrial Revolution, there was kind of maybe 2 or 3 things that humans were doing. We were injecting energy into processes, and we were injecting perception into processes, and we were injecting judgment. As a result of the Industrial Revolution, the piece which was injecting energy into processes, or at least guiding the animals that were doing so, was replaced by electrification and steam. So that did lead to a lot of disruption. There's a lot of debate amongst economic historians about exactly what that disruption looked like. Many economic historians believe that for many decades afterwards, most people were worse off. It's certainly, everybody agrees, it certainly wasn't the case that everybody was better off in line with the massively improved productivity for the next 60 or 70 years. There was certainly a lot of huge problems with basically inequality. But there was something quite handy about the Industrial Revolution, which is that once you have kind of injected energy into processes from electricity or steam, you're kind of done. And so like most technologies, the Industrial Revolution, looks more like an S-curve than anything else. So let's compare that with what the machine learning revolution might look like. And to do so, I'm going to take this exact same chart and I'm just going to change the y-axis in order that I can then draw on top of it what I think the machine learning revolution looks like, because I don't see any reason for that to be an S-curve. Because we know, like in theory, for example, deep learning quite literally, we're aware of no limits to how it can use more data and more computation time to get better. And in general, we're not now talking about replacing energy inputs with some different energy input. We're actually talking about replacing perception and judgment. And once you replace perception and judgment, you can, of course, then use that to create better and better processes and better perception. So there's this kind of feedback loop. And so these are the reasons that I don't expect the machine learning revolution to look like a step function, but to look like an exponential function. So these are like things which I find most people in both business and academia, it's kind of counterintuitive. You know, it's different to looking at history. There's, you know, you've got to be careful about what we can learn from history. And it's also different to kind of how we intuitively think about things. In fact, like an example of this is a lot of people have said, well, the way to deal with this is to invest in education, right? But what happens when you invest in education? When you invest in education, you actually make this line go up more sharply, right? So investing in education might help your kids, right? But it doesn't help the underlying problem. So what's the underlying problem? The underlying problem is that at some point, from first principles, at some point, computers must be better at everything that we do than we are. Unless you believe there's some, human soul or something, which a computer like literally can't have. But if you believe the data, and the math, then at some point the computer becomes better at everything. Therefore, at some point, the computer is better at everything than half of us, right? So what happens at that point, right? So that's actually the problem, the point when computers are better at everything than half of us. So at that point, to put it more precisely, half of mankind can't add economic value, right? And so when half of mankind can't add economic value, you actually have to separate labor from earnings. Because when we assume labor scarcity, we allocate resources on the basis of human labor inputs, and half of humanity can't add economic value with their labor, the system's broken. It's based on an assumption that's no longer the case. So we could, at least in the short term, use a negative income tax to allow that half of the world's economic input to now, have value, at least economically, even if not in practice. Once that stops working, we really have to go to a basic living wage and say, okay, we're now going to totally separate labour inputs, or nearly entirely separate labour inputs from earnings. Eric's told me he thinks that in about 100 years' time, the average, we could basically give everybody about $500,000 a year. My belief is that based on the exponential growth in machine learning, it'll happen quite a bit faster than that. But it actually doesn't matter too much whether you think it's 30 years or 100 years. It's just a time thing, right? So the question is, as long as you accept the premise, then that means at some point, probably in the lifetimes of your children, we're going to have to figure this out. My guess would be we're going to have to figure this out in my lifetime. And in the US, that could be tricky, because in the US in particular, this kind of assumption that, labor scarcity drives a lot of our policy is pretty deep in how we think about things. So, maybe, Europe's already starting to think about some of these things. In places like Switzerland and Germany, you're starting to see actual policy discussion and votes about basic living wage, for example. So yeah, I think that's kind of everything that I wanted to talk about. And I think these ideas about technological unemployment are nothing new conceptually. What I hope might be a new input for you is this idea that deep learning right now is actually, at least in academia, producing algorithms that are better at these key human inputs than humans right now. So in 2 or 3 years' time, you're going to see them appearing in industry. And so, hopefully this can update some of your expectations about what the next 5 to 10 years might look like. So, yeah, if you've got any questions, happy to take them.
So I'm a professor with specialties on computational neuroscience. And so we use deep learning to analyze the exact of serial electron microscopy images to try to map out circuits of neurons in the brain. It's currently pretty time consuming.